Good morning. So in the last from the last class, we had been looking into bridges, most particularly DC bridges. And in the last class, we had seen the Wheatstone's bridge and come to the conclusion that due to the way the components are connected, the Wheatstone's bridge is generally useful for measurement from a few ohms, resistance of from a few ohms to a few mega ohms. Okay, and in case of low resistance, we need to look for other options. So in this lecture, we look into the Kelvin bridge, which is used for low resistance measurement. Okay. So the Kelvin bridge is actually a modification of the Wheatstone's bridge, and it is suitable for measuring resistances with resistors with very low resistances, and because it can take into account the resistance of the connecting leads, and that is incorporated in the circuitry itself. So let's first look at the basic construction of the Kelvin bridge. So in the Kelvin bridge, the construction is very similar to the Wheatstone's bridge. However, the connecting lead between this variable resistance R3 and the unknown resistance Rx, okay, the resistance of this connecting lead is also taken into consideration. Okay, and now the connecting lead is connected. So let us say this resistance is R3, RC, and we really don't know the value of RC also. All we know is that this connecting lead is uniform. Okay, and the galvanometer has a wiper, and the galvanometer can be connected at any point between the points A and B. Okay, until a zero deflection is achieved. Okay, and what is to be noted is that this lead resistance may be comparable to the actual resistance, that is the unknown resistance. Okay, and this is important that because in most cases we don't take into account the resistance of the leads, but in case of Kelvin bridge, the resistance of the lead has to be taken into consideration also. Okay, now if by an appropriate choice of this connecting point C, we are able to now let's look at what is the problem. Because RC is comparable to Rx, not equal to Rx, RC is comparable to Rx. Now how does that affect the entire reading? Okay, now if RC is comparable to Rx and you connect the bridge at this location A, okay, then what would happen is that this arm is R3, okay, and this arm is RC plus Rx. Okay, so if you're not taken into consideration the resistance of this connecting lead, what you would assume is that Rx calculated value you would take as Rx is R 2 by R1 times whatever is the resistance times R3. Okay, but actually what you have is Rx plus, in actual situation it is Rx plus Rab is this factor times R3. Okay, so you are actually, instead of this, you're taking this. Okay, so what would mean that you're overestimating the value of Rx by a factor of Rab. Okay, on the other hand, if you connect the lead at B, the other underestimation would happen. Okay, so if we are able to find a point C between A and B, such that you have RAC, RBC by RAC to be equal to R2 by R1. That is, this resistance divided by this resistance is the same as this resistance divided by this resistance. Okay, now how would that affect? Now at this point C, if you make the connection at the point C and you ensure that the balance is achieved, then you have Rx plus RBC is R2 by R1 times R3 plus RAC. Okay, and how does that help us? If this is done, then because RAC by RAB is R1 by because RAC by RBC is R1 by R2, we can write RAC by RAB is R1 by R1 plus R2 and RBC by RAB is R2 by R1 plus R2. Okay, and that would result in simplifying this first equation and cancelling out these terms that are dependent on this lead resistance, simply because we are assuming that we are able to find a point C such that RAC by RBC is R1 by R2, and this can be slightly easily found if the the resistance of any piece of this wire is proportional to the length of the wire. Okay, that is why the assumption of the wire being uniform was taken. Okay, so if the wire is uniform, then we can say that if AC by AB is R1 by R2, sorry, AC by BC is R1 by R2, then we can simply say that the resistance of the leads can be appropriately compensated. Anyway, if we are able to find this point C, then the effect of lead resistance is compensated and you will be able to just say that the unknown resistance Rx is R2 by R1 times R3. But the problem is that how do you locate this point C? How reliably can you locate this point C? Okay, and how do you maintain the contact at that particular point C? Okay, using a wiper. If because the lead resistance is proportional or lead resistance is comparable to the unknown resistance, any variation here is going to cause significant errors. Okay, so determining and keeping the wiper of the galvanometer at that point C may not be so easy, and that is one problem. The other problem is that what about if the unknown resistance is proportional to the lead resistance? What about the resistances of these parts? Okay, so there may be some RD here. There is some RD here too. Okay, RE here, let us say. And these resistance are being added into the circuit, and we are not really sure how to compensate them. Okay, so that would mean that some further modification has to be done. Okay, in case of very low resistance measurement. Okay, however, when you have resistors of really low resistance, say of 1 ohm or lesser, then you really need to modify the construction of the resistor itself for it to be useful, for you to even rely on the resistor value that is printed. Okay, because any connecting lead, the resistance of the connecting lead would become a significant portion of the resistor's value. Okay, so for this purpose, very low resistances are typically, or precision resistances, they are constructed in a manner that instead of 2 leads, you would have 4 leads in them. Okay, so you have 4 terminal resistances here. Okay, so you have, say, this is an example of a precision resistor. So instead of 2 terminals, there are 4 terminals. You have terminals A and D, which are called as the current terminals. Okay, and you have terminal B and C, which are the potential or voltage terminals. Okay, so the current, the main current that is passing through the resistor is fed between A and D. Okay, and any voltage that is being measured is measured across B and C. So typically when you are connecting a larger resistance, you connect the large resistance across these 2 terminals. You don't connect the large resistance across A and D. Okay, you connect the supply across A and D through A and D. Okay, now this is a diagram of a precision resistor. So you would have this as A D, okay, and you would have this as BC. Okay, now let's go further. Now we can have a modified circuit of the Kelvin bridge called as a Kelvin double bridge, in which you use 4 terminal resistors in the standard arms R3 and RX. Okay, so the current terminals of R3 and RX are connected to the supply and between each other. So these are the current terminals which I am connecting in red. Okay, and the voltage terminals, let me change the pen. Okay, the voltage terminals are these terminals. Through the voltage terminal, you connect it to the other resistors in the circuit. Okay, in addition, you have 2 more resistors, RP and RQ, which are chosen in a manner such that RP by RQ is R2 by R1. Okay, and so as I said, the current terminals are connected to the battery and to each other, and the voltage terminals are used to connect R3 and RX to the other resistors in the circuit. Okay, this is a sort of a schematic diagram of the same 4 terminal resistor double bridge, Kelvin double bridge. Okay, now let us say through appropriate adjustment of R3. Okay, and note that now you only change R3. There is nothing, no wiper here in this RC part, which needs to be changed. Okay, so by appropriate change of R3, let us say that you have achieved balance, that is, there is no current passing through the galvanometer, which would mean that the voltage drop across this path, so the voltage at R is the same as voltage at C, so ESR would be the same as ESAC. Okay, now what would that be? So ESR would be the total battery voltage E times R1 by R1 plus R2 and E is the current, the total current I, the current through this branch I, okay, going through R3 and a parallel combination of RC with RP plus RQ, and another a series combination with RX. Okay, and which would mean that ESAC can be written using this equation. Okay, and from which we can say at zero deflection, since ESR should be equal to ESAC, okay, by substituting the value of E from this equation into the equation of ESR, then you can write this equation, okay, cancel out I and simplify the equation further, okay, collect the terms of Rx to one side, okay, to get this expression. Okay, now we have chosen Rp and Rq in a manner such that Rp by Rq is the same as R1 by R2, which would mean that this part would go to 0. Okay, and that would mean that the equation, the entire equation simplifies to this simple equation, which looks like the equation for a Wheatstone's bridge setup itself. Okay, the only point is that we have to use a 4-terminal resistors for R3 and Rx, and in addition we also need to find Rp and Rq such that their ratio is the same as R1 and R2. Okay, so this is the typical commercially available Kelvin double bridge. Okay, so you already have R3 embedded inside. Okay, and this Rx is the voltage that needs to be connected through this 4 terminals that are here. Okay, there is even a diagram here that shows. So basically what you are doing is that you connect the current terminals of Rx to these 2 ports and the voltage terminals to these 2 ports, and you change R3 by modifying this knob and until you get a 0 deflection in this galvanometer. Okay, and for really low resistances less than 1 mega ohm, the Kelvin double bridge can even be modified to give more precision. So in this case you have a current limiter resistance here, so that the current going into the bridge circuit itself is limited to quite some extent. Okay, then you have this shunting circuit, okay, so that the galvanometer is protected to until near balance is achieved. Okay, and thirdly you have a potentiometer setup here in addition to the variable resistance here. Okay, note that here the potentiometer is giving a standard resistance which changes from 0 to 0.009 ohm in steps of 0.001 ohm. Okay, and you also have a magnetic bar here whose resistance goes from 0 to 0.0011 ohm. Okay, in as a variable resistance would be there, so it can take any value between that, so it can be tuned very finely, and And for a larger variation you use the standard resistance. Okay, and in this manner you can have precision in the micro ohm range. Okay, so in less than 1 milliohm resistances Rx can be measured appropriately. Okay, so these are the two chapters on that can be referred to know better about the Kelvin double bridge circuits or the Kelvin bridge circuits. Okay, and with that we come to the end of this lecture. Okay, in the next lecture we would look into the DC bridge or DC circuits that can be used for high resistance measurement in greater than hundreds of mega ohms. Thank you for your patience.